Hello everyone, welcome to my presentation. I am Dr. Council. Now I am excited to present my project for Bayesian robot in gardening and intelligent decision support system in precision horticulture. In this project, we will explore how probabilistic graphical model can be particularly applied to optimize small-scale agriculture and smart gardening environments. Let's begin by looking at the goal objectives of the work and bridging the gap between abstract probabilistic logic and hands-on agricultural management. Agriculture is inherently unpredictable. Home gardeners and farmers consistently deal with environmental uncertainty, fluctuation, sunlight, erratic weather, and sudden pest outbreaks. Bayesian networks offer a robust mathematical framework to model this causal dependency and uncertainty. By integrating sensor data with expert agriculture knowledge, a Bayesian network-driven system can automate the complex trade-offs, balancing resource usage with optimal crop health to make the truly data-driven decision. To define our scope, home gardeners and small-scale farmers face a complex multivariable challenge. They must balance sunlight, water intensity, and pest stress simultaneously to maximize their crops yields and profits. For this, the project implements a dynamic Bayesian network in the genetical environment to stimulate these exact interactions across discrete time steps. Our core objectives are twofold. First, predictive management that establish a clear causal framework to predict crop health based on stochastic environmental variables, and the second, resource optimization, utilizing utility theory to map out watering strategies that maximize net profit while minimizing unnecessary water expenditure. At the heart of our system is a directed acyclic graph or de-aging. In this graph, nodes represent a random variable. The length or the edge between these nodes represent conditional dependency. For example, the amount of sunlight and the level of water directly affects some moisture nodes without parents at a root nodes, which are initialized with prior probabilities. By updating this probability as new evidence or sensor data became available, the network allows us to model uncertainty and reason dynamically about case and effect relationship. Uh, let's look at the specific decision-based model in this project. We have discrete states for our main variables, sunlight, that can be high, low, or optimal. Water can be excessive, consistent, or deficient, and the pest pressure can be ranging from severe to moderate or none. Uh, Mathematically, the total joint probability of the gardening system is the product of local conditional probabilities as shown in this formula. Here, S, W, and P are our Runo pairs, and M given S and W represent the soil moisture dependency, and H given M and P dictates the final conditional state of crop health. This might be allow us to observe conditional probability logic in action. As we can see, the sunlight and water directly affect the soil moisture, and in the table, for all possible state of soil moisture, wet, dry, and moist, and we have defined a probabilistic and numerical value for every possible sunlight and watery conditional pairs. Similarly, for crop health, it's derived from soil moisture and pest pressure. For opposite pair of soil moisture and pest pressure, we have probability conditional probability value for all excellent, stress, and disease condition under the crop health. Now, this is the full Bayesian network applied for this problem. Let's explore the simulation in the genetical environment. Uh, this implementation will carry out in Netica, where the system architecture is clearly split into these nature nodes and the utility node that represent decision and financial payoff. Netica translate our deterministic engineer equation to probabilistic table and perform the exact interface using junction tree algorithm. Now, if we change from our prior value, it directly affect to the exceeding node. Now the soil moisture value we can see is dynamically changing, and if we change the brush pressure to moderate, now it directly affect to the crop health. Now let's go back to the presentation. So to be continue, uh, uh, we can see the pest pressure remains the highest risk factor in this problem for the plant, regardless of how properly the moisture levels are maintained. To turn this prediction into actionable decision, we integrate a utility function to calculate the net profit. Instead of assuming a fixed outcome, the model applies deterministic logic using the expected utility EU, which sums the probability of each crop health state multiplied by its financial utility. For example, an excellent sheet brings a maximum profit of 500. A struggle brings uh, 115, and if the sea crops the sea, we can be loss of we can have a loss of minus 100. Uh, let's say the expected probability is calculated as 60% of uh, 500 and plus 23% of 115, and then subtract the 60% of hundreds. Then it will leave us the expected profit of 50.6. Our goal is to use smart intervention to maximize this expected utility. Based on the structural and sensitivity analysis of our Bayesian network, I propose three core strategy recommendations for smart horticultural system. The first one is prioritize pest control because the model proves that even flawless watery logic cannot rescue a crop experiencing severe pest pressure. Pest mitigation must be integrated alongside automated irrigation. And the second, implement adaptive watering. The system should dynamically leverage moisture sensors to back up from consistent watering to deficient or light watering when sunlight is low, preventing a soil oversaturation and root rot. And the last one, aim for moist soil status. Cultivating a target moist soil state at as a powerful 90% statistical buffer, maximizing the probability of achieving an excellent crop health outcome and consequently big profitability. In conclusion, by shifting from traditional scheduling currently to a dynamic probability framework, we can actively mitigate environmental risks and optimize resource efficiently. Thank you very much for your time.